Hello, everyone. My name is Brian Zylich, and I am a PhD student at the University of Massachusetts Amherst. Our paper is Linguistic Skill Modeling for Second Language Acquisition. Okay. As we're in an ongoing pandemic, and most of us or many people are studying online via remote learning, intelligent tutors and computer-assisted learning are increasingly popular. And some of these systems are self-paced and self-regulated learning systems. And these systems especially can customize interactions to provide learners with personalized and interventions at scale. But to do this, systems require a model to estimate a learner's current knowledge state. This student modeling problem is well studied for subjects such as math and science, but not as much for second language acquisition, which is the process of learning another language. So that's the focus of our research, is the second language acquisition problem. And specifically, we're looking at the Duolingo system. So some examples of tasks that learners complete in Duolingo are shown on the screen. And these include like translation exercises and listening exercises, for example. So because student modeling hasn't been studied very much in second language acquisition, we looked at prior research which has focused mainly on the role of memory. And so two memory effects are the spacing effect and lag effect. These are popular effects of memory in this field. So the spacing effect says that people learn better through spaced practice over time. And the lag effect says that learning is further improved if the spacing increases over time. So the Pimsleur method is one of the first systems in language learning that takes these two effects into account. And it does this using a fixed schedule with which words are introduced and tested at exponentially increasing time intervals. The Leitner system adds some adaptivity to this method by adapting the spacing based on whether the word is recalled correctly. And you can see that in the graphic here. So when a word is first introduced, it might be reviewed every 1 day. But then if the learner recalls this word correctly, then the spacing is increased to 3 days and 10 days and so on. But if the word is recalled incorrectly, then it goes back to the first bin where it's reviewed the next day. A more recent memory model is half-life regression, which was introduced by Duolingo a few years ago. And this model adds further adaptivity based on the notion that some words are easier to learn than others. To do this, they learn a half-life for each word, which is based on observed recall rates during Duolingo practice sessions. And this is based on the concept of the exponential forgetting curve. So if the half-life is larger, then that means that the word is harder to forget or easier to learn. And if the half-life is smaller, then that means that the word is harder to learn and easier to forget. In other domains, such as math and science, skill hierarchies are more well-defined. As you can see, there's a skill hierarchy here from Khan Academy from math. And items can clearly be tagged with one or more skills. For these domains, skill-based models are more commonly used. So one recent skill-based model is DES3H. And DES3H stands for Difficulty, Ability, Skill, and Student Skill Practice History. And DES3H combines factors such as the student ability, item difficulty, and easiness of each of the skills involved in an item, as well as a skill-based component, which is here represented by the function h, which composes a learner's latent knowledge state relative to each of the skills in the current item, based on the learner's history up to time t. So this function h composes the history using two counters for each skill k in an item j. The first counter is a count of correct tasks completed of prior tasks that share the same skill k. And the second counter is a count of tasks attempted that the prior tasks that, again, share the same skill K. And these counts are computed on varying time windows. So for example, we use the past hour, the past day, the past week, the past month, and in the learner's entire practice history. This model also uses log counts instead of just plain counts to model diminishing returns of repeated practice. So the goal of our work is to explore whether skill-based models are effective in second language acquisition, since they have been shown to work well in other domains such as math and science. The challenge here is that it's not clear what we should use as the skills for these skill-based models. The first thing that might come to mind is, why don't we just use the individual words each as an individual skill? And so this is kind of a naive approach because words can be used in many different ways depending on the context. This ignores grammar knowledge, which is an integral part of language learning. And practicing some words may strengthen or weaken knowledge of other words if they're related in some way. So our approach is to use rich linguistic features as proxies for additional skills. And so we look at three main types: lexical features, morphological and syntactic features, and semantic features. And as a result of using these linguistic features as skills, we see a 21% improvement in word recall probability prediction over prior state-of-the-art models. So the data that we use is from Duolingo tasks. Specifically, it's the data set that they use in the half-life regression paper. And it contains 12.8 million data points from 115,000 learners studying 6 different languages. Notably, the tasks in this data set are split into separate data points for each unique vocabulary item. So even though it may be a translation task, it does not include any context surrounding each item. So we can treat this like a vocabulary retrieval problem. For example, if you look at the highlighted row in the table, it shows that this person is practicing the German word Frau. And this word showed up 5 times within the task, and the learner successfully recalled this word correctly 4 of those times. So they get a recall probability of 0.8. And so this is different from many knowledge tracing tasks where because we have a probabilistic outcome instead of a binary outcome. So our first type of skills are lexical skills. So we look at the surface form of vocabulary words and the lemma of vocabulary words, and we're going to compare these. So the lemma means that a lemma is like a word that represents like a family of words. So you can see like an example here where hermano, which means brother or sibling in Spanish, is the lemma for all of these different variations, which change in the number and gender, but are similar in meaning. Now I'm going to describe our experimental steps so that I can show the results and we can see that lexical skills alone actually provide a great improvement over the half-life regression and other baselines. So there's, as I said, there's 12.8 million data points. We split these into train, dev, and test so that we can tune hyperparameters in the dataset. And then we use the same metrics as the half-life regression paper, which are AUC and MAE, or area under the ROC curve and mean absolute error. And then the baselines that we use are half-life regression, Leitner, Pimsleur, and also 2 constants, which are the mean and the median of the trained dataset p-values. And then we also use deep knowledge tracing because this is a popular recent skill-based model. So deep knowledge tracing uses an LSTM to compose the latent knowledge state. And we make a few modifications for this data set. So we substitute pre-trained word embeddings as the item embeddings. And then we add some additional features at each time step as input to the LSTM. we add the number of correct recalls of at each time step and the number of recall attempts. And then we also add an embedding representation of the time elapsed since the last task, because we have the actual timestamps for each of these tasks. So the loss function that we use, we start with a cross-entropy loss, which is suited for classification tasks and for this AUC metric. But since we also want to predict the actual probability, we add an additional loss term, which you can see here, with the goal of improving the ability to predict probabilities that are between 0 and 1, rather than skewing to either extreme. And this works very well for decreasing MAE while also having getting a better AUC, which we can see here. So the baselines that work the best are the Leitner for AUC and the median baseline for MAE. We note that median baseline wasn't included in the half-life regression paper, but it actually outperforms all of the other methods that were included in that paper. And then, so we first look at the learner item block, which is a simple factor-based model, which includes learner ability and item difficulty. And we can see that the logit loss makes a big difference, decreasing the MAE from 0.18 to 0.114. And this learner item factor model is already able to vastly outperform the best baseline for AUC. And then if we add an additional factor for the language that the learner is studying, this provides another small benefit. And this also outperforms the DKT baseline. We note that we optimize for AUC on the dev set when choosing hyperparameters, because if we optimize for MAE, then we are able to match this median baseline of 0.105. But in practice, this means that our model always predicts a probability close to 1, which isn't very useful. So getting back to those lexical skills, we have the -3H using the surface format skills, and then we have -3H using the low skills. And we see that when we add this, the surface format skills, that means that we are now tracking the skill knowledge in addition to those learner and item factors. So this provides a benefit in performance. And then we find that using the lemma instead of the surface form provides an additional performance, perhaps because practicing that means that more of these items have skills in common, and practicing one word in this family of words may improve knowledge of these other words. So that's the intuition behind this. Our second group of skills are morphological and syntactic skills. We first thought of using subwords because these can be generated in an unsupervised manner using a subword tokenizer. And these subwords may represent noisy morphological features. So, for example, they may contain prefixes, suffixes, verb endings, plural markers, or other subwords that can be multiple words may have in common, which you can see in this table. And on the right-hand side are some examples of subwords that are shared between these different words. And then our second approach was to use syntactic and morphological tags. So these can be generated using a pre-trained supervised model to label words with tags that represent key linguistic features. And these are based on expert linguistic knowledge. So it's likely that they will do better than the unsupervised subword model. And some examples of these tags are part of speech tags, tense, gender, person, case, and you can see some examples here for the Spanish word verb tiene. So here we see that the subword model actually outperforms the best lexical model that we had before. So it does provide some benefit. But not surprisingly, the models that use the expert-derived linguistic tags are even better. So our final type of skills are semantic skills. And the motivation for these are that practicing semantically similar words may reinforce knowledge of similar words, which we call constructive interference, or they may cause confusion between different words, which we call destructive interference. And the way that we implement these are by changing how we calculate the counts of attempts and of correct, And so to do this, we when we are implementing these counters, now we look at all tasks in the user's or the learner's practice history, rather than just the tasks that share a skill. So to do this, we define a semantic similarity function between between words. So that the current word and all words that the learner has practiced in the past. And for the attempts, we just use the similarity function. And for the correct counter, we use the similarity function multiplied by the recall probability at that time. If you're not familiar with semantic word embeddings, these are what we use to do this similarity function. So semantic word embeddings represent are a vector representation of the meaning of words. And so the idea is that if words are closer in meaning, then they should be closer together in this high-dimensional vector space. So the first semantic similarity function that we use is cosine similarity. And this is a simple approach, but it only models constructive interference. And one disadvantage is that it's less flexible. So these semantic word embeddings are derived from a language modeling setting, but we're looking at more like a memory setting. And so these these might not line up. So we introduce a neural network and create a neural similarity function. And this is more flexible because it doesn't, it decouples the language modeling and memory settings. And we use a tanh activation function so that it can model both constructive and destructive interference. So we see that the cosine similarity approach actually decreases performance, but the neural semantic similarity function results in our best model with a 21% improvement over the state of the art. In conclusion, using lexical, morphological, syntactic, and semantic features, we decompose each word into a series of skills. With the -3H model that makes use of multiple skill tagging, we leverage these rich linguistic skills to improve predictive accuracy. In future work, we hope to explicitly capture the constructive and destructive interference effect of semantically similar words on memory, and further understand the relationship between word similarity and time difference in a learner's practice history. Some limitations of the study are that we did not try all combinations of our 3 types of skills. For example, we did not try combining morphological and syntactic skills with semantic skills because the model structure for each of these was substantially different. And we also note that the data does not include context surrounding each word. So even if these items may be coming from translation tasks, we don't have the context which would be useful for predicting whether they got that word correct or incorrect. And this is something that we're exploring in ongoing work with a different data set. Thank you everyone for coming. If you have any questions, I'd be happy to answer those.